Hello ATS 114 students, welcome to Lab 10, the class today about mid-latitude cyclones. And I think you're going to enjoy this activity. It kind of builds on what we did last week with regard to reading weather maps and so on. It's kind of probably pretty close to the kinds of things you sort of expected to end up doing in a class called Introduction to the Atmospheric Sciences. So let's take a look and see what's in this lab activity. First of all, there's going to be a map about a particular mid-latitude cyclone that you're going to be studying in this particular activity, a case study as it were. And there's sort of a mid-latitude cyclone with its attendant cold front and warm front and so on. And you can see the counterclockwise rotation around it. And the problem is asking you in the book to label the air masses. Don't make this more than it is. Basically what they're saying is, for example, to label this area in the warm sector, that region between the cold front and the warm front, as a maritime tropical air mass, because of course it's coming off the Gulf of Mexico in this case. And then to do the same sort of thing for two more locations, what kind of air mass is behind the cold front? What kind of air mass is ahead of the warm front? That's all they're looking for. They're not looking for any, more details other than just the two-letter code for each of these types of air masses. Now there's a series of weather maps that I think require a little bit of clarification as to what the question is asking for. If I just kind of zoom in on one of these diagrams here, you see this area of low pressure, this cyclone centered just north of Texas in this particular case, and there's 4 locations marked with stars there. What they want you to do is, it says to draw the winds there using a standard wind symbol. What they mean is they want you to use that wind barb symbol. You don't need to worry about the wind speed. That's a little bit more than you would need to worry about this time, but you do want to draw the wind barbs. Remember, barbs point upwind, and then they have a little flag on the end of them like that. And let me give you a hint as to how to best draw them. Like I have them on this map right here, see how they're basically, the winds are basically parallel to the isobars? Start with that, but then realize, oh yeah, winds at the surface are actually not quite parallel to isobars. They're sort of rotated about 30 to 45 degrees from parallel, such that they're spiraling in towards the center of the cyclone. So they want you to draw a total of, I think it's 12 of these little wind symbols over a series of 3 maps. And then based on that information, they want you to look on the other half of that diagram where they have a sequence of station models. Now each column of, again the instructions aren't so clear about this, each column of that, in that chart represents one station. So like where I have one in blue, one in green, one in yellow, one in pink. That's each one station. It's just that one of those is A, one is B, one is C, and one is D, but they're not necessarily in order. So once you have drawn your wind barbs at each of those 4 stations for the 3 times, go back and look then at these station models and say, oh, I see, let's just say A has to be the yellow one, or B has to be the green one, or whatever it is. I haven't made the key yet. Okay, so you're going to be doing the same sort of thing then on a larger scale with some maps of a mid-latitude cyclone, and they're going to have you doing things like compare the stations that you see on either side of the cold front. I think it's the cold front, it might be the warm front. So you have a station, a weather map that looks like this, and they want you to notice things like what is the temperature ahead of the cold front? What are the typical temperatures behind the cold front? What is the typical difference between the temperatures ahead of the cold front and ahead of the warm front, behind the cold front? What are the typical difference in the dew points ahead of the cold front and behind the cold front? Stuff like that. So again, they're not really overthinking type things. They just want you to kind of come up with what are the typical differences on either side of the front. Here's some diagrams that are, there's some examples of this actually in your textbook, but I don't think in my section of the course anyway yet we have actually used this term meteograms. Meteograms are diagrams that show meteorological information at a particular station with respect to time. So if you look down here at the x-axis of this diagram, you can see that these are actually times along the bottom here. Now the notation's a bit weird. So like it starts at 9/0300, okay, that would be 3 o'clock, actually it's UTC, or Greenwich Mean Time, or whatever. Oh no, I'm sorry, the key actually does say Central Time. So 3 o'clock in the morning on the 9th, and then the next little line over is 6 o'clock in the morning on the 9th, all the way over to the 12th. Okay, so there's about 3-4 days of meteorological data along the x-axis there. And the only trick on here is to make sure that you're using the right axis for each of these diagrams here. Pressure is on, I had drawn the trace of the pressure at that station over that period of 4 days, and you can see that it uses that pressure scale. The temperature and the dew point both have units of temperature, like degrees Fahrenheit, so they both use the same scale over there on the left side of the diagram. and the precipitation are these little bar graphs along the bottom, and they use the scale over on the right-hand side of the diagram. But once you have figured out how the diagram is laid out, this is just reading a chart. It's not terribly difficult. And what this diagram is particularly useful for is to recognize when changes happen at a particular station. In particular, in the lab activity today, you're going to be identifying frontal passage events, when fronts went past a station. And so like in this particular case, I pulled up the diagram for Birmingham from your lab manual. And you can see how at the time that I have indicated with the red arrow there was a big change in the winds. See how the winds were out of the south, and all of a sudden, you know, at the next time they're out of the west, and over the course of the next few hours they even turned to the northwest. Look how that was the highest temperature, and then the temperature started trailing down. See how the dew point started trailing down. See how that was when the rain happened. That is a frontal passage event. In fact, it's probably a cold front that went through Birmingham at that time. You can be doing the same sort of thing with, I think it's Indianapolis, on your lab activity. Now there's one other idea that comes up a couple times in the second half of the lab that bears mentioning. And this is this term that we've certainly used several times in the class, but we've probably never actually talked about exactly how to find it on a weather map, and that's advection. Advection is transport of a property. We can talk about like moisture advection, or we can talk about I don't know if all the sections of the lab yet have done the property of vorticity, but you can move vorticity with the wind, and then you have vorticity advection. Well, in your lab activity, you're going to be talking about warm air advection and cold air advection. Transport of cold air towards someplace that's warm, or transport of warm air towards someplace that's cold. That's warm air advection. And you're going to be doing it using an 850 millibar chart. Now, your chart in your lab manual is in black and white, not in color like this one, but this one will help us learn what's going on. Remember, an 850 millibar chart is a map of how high above the ground you have to go to reach a pressure of 850 millibars. And on a chart like that, well, you have a chart just like that on page 125, but on a chart like that, we can start thinking about the forces and what the winds are doing, and then in this case, the colors are about temperature and so on. Just to show you, though, what's going on with regard to warm air advection and cold air advection, let me zoom in on this cyclone that is centered in western Kansas here. Now, we have these solid contours here that are going to be telling us something about the winds. And we're going to be using these solid contours, which are telling us something about the, well, they're actually the heights, but since we can assume the winds are geostrophic, they're going to be telling us something about the winds. And the colors in this diagram, which are telling us something about the temperature, to tell us something important about how there is advection going on. The transport of some property, in this case cold air and warm air, by the winds. So we're going to be looking for areas of cold air advection and warm air advection. Alright, well, as I said before, the solid contours on here are contours of 150 millibar height. They work very much like isobars. We can then assume that because the winds are going to be geostrophic, that we can say that the winds are going to be parallel to those solid contours. And in fact, this particular color diagram that I got off of a website even has little arrows on there drawn to represent what the winds are doing. And you can see they're basically parallel to those height contours, which work basically the same as isobars. 850 millibars is about 1.5 kilometers above the ground. It's high enough above the ground that we don't need to worry too much about friction and things like that. Now, the colors, of course, are referring to temperature. Now, if we take a given location, like this location in kind of north-central Texas there, look what's actually happening. There's winds coming towards that station from the west. We can either figure that out by looking at those little vectors, or by just remembering that the winds are going to be parallel to those solid contours. And as those winds are coming towards that station that I have marked with a star, they're bringing colder air with them. There may be other processes that work too, but barring everything else, the temperature of that location is going to go down because we're transporting colder air towards it. Okay, we are experiencing cold air advection at that location. And the same way if we pick this place in central Iowa here, where I have them marked by a star here, again, we know the winds are basically parallel to those solid contours, and we can see how the winds are bringing warmer air from the south towards that location. We're currently at like a green color on the map, but yellows and oranges and reds are coming. That area is experiencing warm air advection. See how the colors really helped? They helped us understand what was going on, but that's actually not mathematically what we did to actually figure out whether there was advection going on. Graphically, what we see here is that the different kinds of contour lines on this plot are crossing each other. We have the solid contour lines, and they are crossing the little boundaries between each of the colors on the map. When the contour lines are crossing each other, we can start thinking about advection. In particular, what we want to do is we want to see these little diamond shapes that form when two sets of contour lines are on the same plot, and they make these little diamond shapes. Those little diamond shapes are called solenoids. And those little diamond shapes are actually proportional, inversely proportional actually, to the amount of advection going on. The smaller those little diamonds are, the smaller those little solenoids are, the more temperature advection in this case is going on. So as long as we see some pretty small little diamond shapes on these contour maps, that is an area where temperature advection is happening. So in this case, I see that there are basically two big areas of temperature advection. I can see that there's an area across like Texas and Oklahoma and maybe Kansas where there are little solenoids, little diamonds being made where the contours of temperature and the contours of height are crossing each other. And if I think through which way the winds are blowing and how they are moving air of different temperature, we see that that is an area of cold air advection. Meanwhile, out there across like eastern Nebraska and Iowa and Illinois, we again have temperature contours and height contours that are crossing each other. We see the little diamonds, the little solenoids, and that tells us that there is some kind of temperature advection going on. And again, if I just pick a location and I see which way the winds are blowing and what is the temperature of the air that's coming our way, we can see that this is an area of warm air advection. So just by looking at these little maps with the contour lines on there, we can actually identify where there are areas of warm air advection and cold air advection on the plot. Now, synoptically, or when we're talking about like a weather map, it turns out that generally speaking, the areas of cold air advection and warm air advection happen on the poleward side of the polar front. Both cold fronts and warm fronts are examples of polar fronts. And we're going to see that on the side more towards the poleward side, is where the temperature advection is going to be. In fact, meteorologists often will use plots like this to find areas of cold air advection and warm air advection as sort of a first hint as to where they should be looking for cold fronts and warm fronts when they are analyzing a map to make a forecast or something like that. You expect the cold front and the warm front to be just a little bit equatorward of where the warm air advection and cold air advection would be. Now, your lab manual says that warm air advection tends to be associated with rising motion and cold air advection tends to be associated with sinking motion. That's true. I would have not said that because I think it's a little more complicated than that, but broadly that's true. And so if we have an area of warm air advection happening out ahead of the warm front, we're going to generally expect cloudiness out ahead of the warm front. Whereas, like, if there's cold air advection behind the cold front, we're going to expect sinking motion and clear skies behind the cold front. There might be clouds out ahead of the cold front where the cold front is lifting air up as it plows its way forward. But behind the cold front, there'll be an area of cold air advection that produces sinking motion. Okay, it's actually somewhat more complicated than that, but that's a good first guess as to how to associate cold air advection and warm air advection with whether or not there'll be clouds and precipitation and so on in a given region. Now, in your lab manual is printed in black and white. You don't have pretty colors of temperature, but it turns out you don't need them. As long as you have two sets of contours on the plot, where the solid ones are height, which works a lot like pressure, and you have like dashed ones, which in this case are temperature, yeah, it's a whole lot to be seeing on here, but you're not really taking in the pattern. You're just looking for where are there little diamonds. And so, like in this case here, I don't remember which hour this happens to be in your book, but we can clearly see that there are areas like across Oklahoma and Kansas and Missouri where there are little diamonds, and you can see other areas where there are across like Michigan and New York and so on. That's what they're looking for here. You don't need the colors, you just look for the little solenoids in the pattern. Okay, that's actually all you need for this lab activity. I'm not anticipating this one actually taking terribly long. I think you guys are going to be in good shape, and your TAs are well trained. They know how to answer your questions about this stuff, and I look forward to seeing you next week.